Hello. All right, today we're going to talk about kind of a high-level overview of how we're going to transform some objects into world space in a way. So we're really just going to look at manipulating points, what that means for them, very simple definitions of what we can do to them, and we'll play around with a couple quick, simple examples, and we'll get into some more depth and talk about matrices in the next episode. So let's move over to the board. Okay, so simply put, we could just say that if you watched the earlier tutorials, you saw we wrote a quick line rasterizer using the naive line algorithm. So we can pass it 2 points, point A and point B in the screen space, and it will just draw a line between 2 points. So that would mean that what we're going to look at as far as objects are concerned at the moment, let's just say that objects just consist of a list of points. And we're going to refer to those points as a vertex, or vertices, or vertexes. All definitions work. Vertices and vertexes are interchangeable. So if we had some kind of, I don't know, like a rectangle squarish object, we can define it with just the points. And we could say that this is, I don't know, point A, U can be B, C, and D. So if we pass these points, let's say they have some type of coordinates in our world, don't worry about what they are mathematically, but we can say that, let's say we pass A and B to the rasterizer, right? Then B and C, and then C and D, right? Then D and A. Okay. If we passed these to the rasterizer, well, it should be obvious, right? That we get that would be drawn first. Then we would draw a line between B and C, then between C and D, right? Then between D and A. So once those have been drawn, now we have this actual, visual representation of a square or rectangle-ish, object. So we could say that we could define, objects to be like, I don't know, a list of points. Okay. So if I sent these to the rasterizer in a certain order, I could get it to like draw that one and then that one and that one, like this. And then a line, maybe a line between those two and a line between those two. Then we would have this. Okay, and we'd have a really terrible smiley face. But nonetheless, we have the makings of being able to construct outlines of different, types of objects. In more simpler terms, we could have something like these 4 points, and we can pass them the same 4 points, only pass, right, only pass AC, right, and BD, and instead now we would get an X. So the same 4 points can create two, many different objects, not two, obviously, but you can do whatever you want with them. So we're really going to look at these transformations of how we can do things to this square, like rotate it or scale it or translate it. Then we're really just doing it to individual points. We're going to rotate, scale, or translate this point around or about a certain axis, and as a result, when we do that same operation on all points A, B, C, and D, well, then we get a definition of a new object, which is a modified version of the existing one, which is really all we're doing with transformations. So let's look at how we would go about it. So if we had an axis, so here's our axis, and okay, and we'll make our square. So I'm going to show you, let's say we're defining our square in model space right now. Okay, that's how we're gonna draw them. So here's our square, and let's say that he's a width and a height. Right, so his width is 1 and his height is 1. This actually means that this point up here, and we're defining him out of these 4 points, just like I mentioned. So this point right here is actually at 1/2 and 1/2, right? 1/2 on the x and 1/2 on the y. 1/2, try that again. 1/2, right? And 1/2. Because he's a length of 1, he only goes half out to the right, and then negative 1/2, and 1/2 is this one. Negative 1/2, negative 1/2, right? And 1/2, negative 1/2. So this creates a square object made out of 4 points in model space that, represents a square. So simple. Now let's talk about our transformations, right? I said that we can scale, we can rotate, and we can translate. So let's look at scaling, okay? So scaling, to scale something, you just take the point, right? So our x prime, whenever I say prime right now, I'm referring to the result after it has been modified. So our new point, x prime, is going to be equal to some scalar value, which we're going to say some x scalar value, right, multiplied by the original x. So this guy right here, let's say we're looking at this point, we could say that his new x prime is equal to some scalar value multiplied by where he's at now, which is 1/2. So we'd be multiplying the x component of this point or vertex, right, by some scalar, and that's going to result in it moving on the x-axis to the right or to the left based on how much we've scaled it by. And similarly, y prime is just some y scalar value multiplied by the original y value. So it's the same thing. So the really simple example could be that if we choose s of x and s of y to be 2, well, what we're doing is taking 1/2, right, and we're multiplying it by 2. And we're taking this 1/2 and multiplying it by s of y, which is also 2. If we multiply those two by 2, right, we get 1 and 1, which would take this point twice out here and twice out here. The point would now be here. If we do this to all 4 points, right, then this would go out twice as far, this would go out twice as far, this would go out twice as far, and you'd see that, we have a square that's twice as big as it was before. Okay, so that was just a really quick way to show that. All right, so that's what scaling does. It's simple, it's intuitive, it makes perfect sense. We multiply it by a scalar, hence we scale it. Done. Okay, so that's how we can modify it that way. Then we can also, we're going to look at translate now because it's easier. So we can translate an object as well. And translating it is not much tougher. The result, x prime, of a translate is just equal to the initial x plus some value a. Okay, and y is the result of the initial y plus some value b. So we're saying that a is equal to the value that we want to translate the x by, and y is equal, or b is equal to the value we want to translate y by. And by translate, I mean move. That's it. To translate an object or a point or a vertex is just to move that vertex. So for example, if we were to say, let's make a 1 and let's make b 0, okay? So if a is equal to 1 and b is equal to 0, we're saying we want to move all x points, all x vertexes, 1 over, right? We're adding 1 to each x. And in the y, we're adding nothing to it, so y remains unchanged. So this would take this thing by 1/2 and 1/2, right? We'd be saying 1/2, right? X prime is equal to 1/2, right? Plus a, which is 1, which is just 3/2. Okay, so 3/2. And y prime is equal to 1/2 plus 0, which is just 1/2. So if we move this out to 3/2 and 1/2, right, we'd be moving it by its entire width, and this guy would end up out here, right? That would mean that this guy, negative 1/2 plus 1, right, is just 1/2. Same here, and same here. But we didn't move up and down at all because we didn't translate on the y-axis. Which means, our square after moving over would end up looking like that. we moved it to the right. So this choosing an A of a positive value and choosing a Y of nothing just means move my object to the right, but we didn't adjust its scale. It's still the same proportion, it's still the same size as it was before, hence why we're just translating it. Okay, so that's translation in a nutshell. And lastly, we have our rotation. Now rotation, I'm going to write it first, and then we're going to derive it because it's the only one on here that's not so intuitive. Like this makes perfect sense, and so does the scale. But as far as rotation is concerned, it's a little weirder, but it'll make sense after we derive it. Okay, so rotation will look like this. So this is the result of the rotation, right, is equal to the original x multiplied by the cosine of the angle that we're rotating by, right, minus the original y multiplied by the sine of the angle, okay, and the y after it's been transformed is the original x multiplied by the sine of the angle plus the original y multiplied by the cosine. Okay, so now that we have this crude definition that I just pulled out of nowhere, we'll show really quick where it came from. Let's do over here. So we'll take an axis, okay, like so. Now let's say that we have some point out here. Let's put him here, okay. And this point is the result of, let's put him there, of some kind of rotation, some kind of original rotation, okay, by the angle alpha. This is some angle alpha. Okay, so we rotated, right, the axis by the angle alpha, and as a result we got some point out here that has the coordinates x, y, right? It has some x and some y. We're saying that this is our original point. We're just pretending that it's the result of an initial rotation, okay? Even if that rotation were, say, 0, wouldn't matter. All right, so given this, right, what is the value of x and what's the value of y? Well, we're going to use just simple trig for this, right? We have this right triangle here, okay, and this right triangle would say that, you know, our x is going to be, and before I mention anything else, there is no, the radius is 1, okay? This is the unit circle that I'm giving this example on. So we know that x, right, this x is simply, right, the cosine of this angle alpha, okay, and y is the sine of this angle alpha, okay. So now we know our x and our y coordinates. Now from our starting point, let's say we rotate by some angle theta, okay. There, we have now rotated by some angle theta. Cool. So that will give us this rotated point out here, right? And this point's going to have the coordinates x prime and y prime. So we're saying the coordinates of this point are the result of a rotation by some angle alpha to get to the initial point, and then another angle theta, so theta more, to get to the point x prime, y prime. Okay, so that would mean, right, that x prime is equal to, and now we're just going to look at this is trig again, right? There's this little right triangle right here. We know that the total angle, right, from the beginning of the axis all the way to x prime, right, to get to here is just the combined angles, right? It's just alpha plus theta, right? Alpha plus theta is this whole single angle right here. So that would mean that we get simply x prime is cosine alpha plus theta, right? If we go the whole angle and then we take the cosine of it, we get this x value right here, which means that y prime is equal to the sine of alpha plus theta. Simple. Cool. So we have this. Now we're just going to use some identities to make this a lot simpler by expanding it first and then making a couple substitutions, and we'll be right there. So I'm not going to go over the trig identity for this. You should know these, and if you don't, just look them up, like the addition angle, how you can expand when you're adding two angles together, and it's the following. So cosine alpha plus theta is the exact same thing as saying cosine alpha multiplied by the cosine of theta, right, minus the sine of alpha multiplied by the sine of theta, okay? And y prime is the same, and sine alpha plus theta is the same as saying the cosine of alpha multiplied by the sine of theta plus, right, the sine of alpha times the cosine of theta. Okay, so these are equivalent statements right here. And we do this trick because then what we can notice is, because I said that our original points x and y over here on the right are the result of some rotation about alpha, we were able to define the cosine of alpha, right here, the cosine of alpha and the sine of alpha, to be x and y, which means that in here, this equation, we can just substitute anywhere we find cosine of alpha. Since it's equal to x, we will replace it with x. So this will get replaced, right? And anywhere we have sine of alpha, we can replace it with the original y value, which gives us what we were hoping for, right? Our x prime then is equal to, here's cosine of alpha, so that's x multiplied by the cosine of theta, right? Minus our sine of alpha, which is just y, multiplied by the sine of theta, and our y prime is equal to x sine theta plus y cosine theta. Now what does that look like? Well, now we have shown that this and that are equivalent. So this is where it comes from. All the ambiguity has been stripped away. Except, as you could be asking, where did this alpha come from? And if you were listening before, I had mentioned that this angle alpha could be 0. So in reality, we could be at right here and right here, right? This angle alpha is just equal to 0, which means that no rotation occurred. So then we rotate by some theta, right? And we rotate by some theta, and it's still the same thing, because we end up replacing this x equals cosine alpha with just x. So it doesn't matter if alpha really was a rotation or not. But to show it, it's easier to see if you actually did rotate by some alpha and then some theta, and this helps you see this derivation right here. So that's it. This should give you an idea of how you can take this object here that's defined by a list of vertexes, right? If we were to perform some scale on it and get a new value, and then some translation, and then some rotation, we'd end up with a brand new value for everything. And maybe we had these points now, maybe they're out here, and they end up looking, right, like some object sort of like this. This looks to me like an object that started as this, was rotated, right, by a certain angle, I don't know, maybe 45 degrees or so, right, and then scaled only by the y-axis it would have been scaled by, because it got longer, right, and who knows if it was translated, because I'm not showing you the axis. But see, this came from this original model, right? So then we'd have these new coordinates for points, A, B, C, and D, and when we pass it to the line rasterizer, it'll draw these lines, and now we have this square or rectangle that has been positioned somewhere in a world as the result of starting with its model and scaling it and rotating it and translating it until it's been put now into a world with all of these other objects. And this is an example of the what happens specifically to these points or vertices to get it into this model space. All right, so that's it for now. I'm gonna do another post shortly on. We'll do a video explaining where the matrix comes from for each one of these, and why the matrix math is going to be a lot more helpful when we're actually trying to perform these transformations. And the hint is that when you concatenate matrices together, or matrices, every time you multiply them, you get a new matrix that's a single one that actually is the combined scale, rotation, translations, or whatever. It's all the combined transformations that you wish to do in one single matrix, and that's a really good, nifty thing to use. So we'll go over that the next time I make a video, and stick around. Thanks.